Bismillahirrahmanirrahim. Dear students, today we will be solving a couple of problems related to shear force diagram and bending moment diagram. In last class, we started our first problem. We could not complete that. So today I will start by reviewing that part that we discussed in last class, and then we will complete this problem. So this is our example number one, and in this problem we have a simply supported beam subjected to a single point load at point B. Span of the beam is 10 meters, and the point load acting is of magnitude 10 kilonewton. The location of the load is at mid-span, 5 meters from support A. As we discussed earlier, that the first step in solving a beam is to calculate the reactions of the beam. So let's see how to calculate the reactions. This is a determinate beam, and we will be applying conditions of equilibrium to calculate the reactions. Now, how many reactions will be generated in this case? We have a hinge support here, and we have a roller support here. A roller support will generate one reaction, let's call that RC, and hinge support, although it does have the capability of generating two reactions, but it will generate one reaction only. Why? Because there is no horizontal load acting on the beam, so there will be no horizontal reaction. There will be only vertical reaction. So there will be two reactions in total, vertical reaction at support A and vertical reaction at support C. Now let's apply the conditions of equilibrium. Sigma Fy equal to 0, and it is recommended to write down convention whenever you are applying the condition of equilibrium. So for sigma Fy equal to 0, our convention is upward forces will be taken as positive. Now let's start from this side. Ra, it's acting in the upward direction, so it is positive. Then 10 kilonewton force acting in the downward direction, so negative 10, and plus Rc because it's acting in the upward direction, and this sum should be equal to 0. If we rearrange the equation, we get Ra plus Rc equal to 10. Now in this equation, we have two unknowns, so we cannot solve this. So let's label this as equation number 1 and move on. Next step is to apply the second condition of equilibrium, sigma mc equal to 0, and for this our convention will be clockwise movement will be taken as positive. Next, let's apply this condition. Now if we start from here, this is our movement center, so Ra into 10 is the lever arm, and this movement will be in clockwise direction. So according to our convention, clockwise movement is positive. That's why we have taken it as positive. Then this 10 kilonewton force, it is producing movement in counterclockwise direction about point C. So it should be taken as negative. 10 into 5. 5 is the lever arm, the distance between the perpendicular distance between load P and point C. So 10 into 5. Is there any other force present in the system? There is a third force, Rc, but Rc is passing through point C. So the lever arm for Rc with respect to point C is equal to 0. Therefore, it will not produce any movement about point C. We already know this from our basic mechanics that if any force passes through a point, it cannot produce any movement about that point. So that's why this equation will end here. We'll put it equal to 0. And now in this equation, we have only one unknown, Ra. So if we rearrange this equation, we get Ra is equal to 5 kilonewton. Next, if we put this value of Ra in equation number 1, we get Rc equal to 5 kilonewton as well. Now at this stage, we can try to verify that whether our reactions are correct or not. So there are a couple of observations about this reaction. First observation is that this magnitude of reaction or the sign of reaction, both the signs are positive. Ra is positive 5 kilonewton and Rc is also equal to positive 5 kilonewton. So both the reactions are positive, which means that the directions that we assumed at the beginning were correct. So directions are fine. And secondly, both the reactions are equal in magnitude. Now, if we look at the situation, there is a point load acting at the center, and we have two vertical reactions at the extreme end. So the beam that we are analyzing is a symmetrical beam. The system is symmetrical. So it is very logical that this load will be divided into two parts. Half of the load will go here and half of the load will go on the other side. So RA and RC both are equal in magnitude and in opposite direction. So this seems fairly logical. Okay, so this was the reaction calculation. And next step is to divide the beam into number of portions. And we discussed earlier that we divide the beam into portions depending upon the applied loading and support conditions. So wherever there is a variation in applied load or there is a change in boundary condition or end condition or support condition, we divide the beam into portion at that point. So if we start from point A and we move towards point B, we do not observe any change until we reach point B. At point B, we have a point load. So this part AB can be considered as one portion. And then if we move further from B to C, we see that there is no change from B to C until we reach point C. So this part BC can be considered as another portion. So for this beam in total, we will be considering two portions, AB and BC. Now, once the portions are defined, next step is to consider these portions one by one and draw their free body diagram and write down the equations for shear force and bending moment. So let's see how to do that. All right, here we are. So first portion is portion AB, and the range of X for portion AB is from 0 to 5 meters. If I come back to this picture, this figure, whenever we divide the beam into portions, in every portion we have to consider a section. So in portion AB, we will consider a section, and this section will be at a variable location, and the variable will be X, starting from the extreme left side. This is one section. And similarly for portion BC, we will have to consider one section. And again, this section will be labeled from the extreme left side, and the distance is variable and the distance is labeled as X. So for portion AB, this is a section, and for portion BC, this is a section. Now let's come to portion AB. Okay, here is portion AB. So X starts from 0 to 0.5. 0 is point A and 5 meters is point B. Here is the free body diagram of portion AB. We have a hinge support at left end, and then we have a section at a distance X from support A. 5 kilonewton reaction is known at support A, and as we already know that the dominant internal forces in beams are bending moments and shear forces. And these forces are not visible, but when we cut a section through the beam, then these forces get exposed. So whenever you cut a section through a beam, you need to mark the shear force and bending moment. And these forces can be marked in any direction, but in our case, we will be following one convention, that we will always mark shear force in the downward direction and we will mark bending moment in the counterclockwise direction. These conventions are not absolute truths, and these conventions can be changed, but it is recommended to decide a convention at the beginning and stick to that convention. We can change convention from problem to problem. We can follow one convention in one problem and we can follow a different convention in another problem. But if we keep on switching the convention, it leads a lot of confusion. That's why I want you guys to stick to one convention. And another important point to note is that although we can change convention from one problem to another problem, but we cannot change convention within a problem. So if for portion AB, we have decided that, okay, we will be taking shear and movement in this direction, we cannot change this for portion BC. Once a convention is fixed for a problem, it will remain fixed for that problem. Otherwise, you will get misleading answers. However, from one problem to another problem, the conventions can be changed, but I don't recommend that either. Okay, now once we have the free body diagram, then we write down the equation for shear and bending moment. For shear force acting in y direction in this case, we apply sigma Fy equal to 0. Now, how many forces are there in vertical direction? 5 kilonewton force is acting in upward direction. Our convention is upward positive. So 5 minus V is acting in downward direction. So if we rearrange this, we get V is equal to 5 kilonewton. Now we have got a fixed number for V in this case, which shows that the shear force is constant for portion AB. There is no variation in shear force as we move along X for portion AB. In some other problems, we will see that the situation will not be like that. We will encounter that situation in future. Next is to write down the equation for bending moment, sigma mx equal to 0. We will write down the equation for the section at distance x. That is why we are calling this mx equal to 0. Our convention is clockwise is taken as positive. And we will take the moment about the section. This 5 kilonewton force will produce moment in clockwise direction about this point. So 5x is the moment of this force about the section. And then this m is in counterclockwise direction. So minus m, and that is equal to 0. Now, what about this force V? Will this produce any moment about the section? No, it will not produce any movement about the section because it is passing through the section. So the lever arm is equal to 0. So 5x minus m equal to 0 is the equation of movement. Now let's rearrange this. We get m is equal to 5x. This time in the expression for movement, we have got the variable x, which means that as x is changing, the moment is also changing along the length. So let's put x is equal to 0 and x equal to 5 for the two extreme ends of this portion. At point A, x is 0. At point B, x is 5. So in this equation, we put the value of x, and for point A, we get moment equal to 0. And for point B, we get moment equal to 25 kilonewton meter. Okay, so this was for portion AB, and now let's see portion BC. This is a free body diagram for portion BC. Now, one clarification here is some of the students think that when we are talking about portion BC, we will only draw the free body diagram of portion BC part. But if you recall the basic definition of shear force and bending moment, for shear force, we said that it is the algebraic sum of all the transverse forces acting either on the left side of the section or on the right side of the section. Similarly, for bending moment, we said that the moment should be, it is the algebraic sum of all the moments acting either on the left side of the section or on the right side of the section. Which means that we need to consider the entire part of the beam either on left side or on right side. We cannot just consider portion BC. Okay. So here is the free body diagram of the entire left part of the beam with respect to the section. 5 kilonewton force acting in the upward direction, 10 kilonewton force acting in downward direction. Location of section is X, and these are the internal forces, shear V and movement in counterclockwise direction. X ranges from 5 to 10 meters. Sigma Fy equal to 0. If we apply this equation, we get 5 kilonewton acting in the upward direction, 10 kilonewton acting in downward direction, and V is acting in downward direction. If we rearrange this, we get V equal to 5 kilonewton with a negative sign. You need not to be worried about this negative. We will incorporate this negative sign when we will draw shear force diagram. We will see that in a short while. Next is sigma mx equal to 0. Our convention is again clockwise positive. Now this 5 kilonewton force produce clockwise movement about the section. So 5 into x is the lever arm. 10 kilonewton force produces counterclockwise movement, so it is negative. And how much is the lever arm? If this much distance is x and this much is 5, so the perpendicular distance between the section and the force is x minus 5. So minus 10 into x minus 5. And m is acting in counterclockwise direction, so minus m equal to 0. And if we rearrange this equation, we get m is equal to 50 minus 5x. Then we put the value of x for point B and point C. And for point B, we got the value of moment as 25 kilonewton meter. And for point C, we got 0 moment. Now, the important points to note at this point are that at point A, we got the value of bending moment as 0. At point A, we got moment as 0, and at point C we got moment as 0. So is this logical? Yes, this is logical because at point A and at point C we have roller and hinge supports, and we know that at hinge support and at roller support there can be no bending moment. That's why we got 0 values. And for point B, we got the value of bending moment equal to 25 kilonewton meter from both the sides, from side AB as well as from side BC. This is also logical because there is no point moment acting at point B, so the value of moment should be same at point B from either sides. In some cases, we will see that the value of there will be a point movement at a given point, and for that point we will have two values of bending moment for a single point. We will see that situation later on. So this was a review of part of the problem that we solved in last class. Now the next step is to draw shear force diagram and bending moment diagram. So let's do that right now. All right, so for this, first of all, I will draw shape of the beam. This is the beam, simply supported beam, and a load of 10 kilonewton is acting here. This total span is 10 meters. This distance is 5 meters, and this is also equal to 5 meters. This point is point A, and this point is point B. And we know the reaction here. Reaction is 5 kilonewton, and reaction here is also equal to 5 kilonewton. Okay. Now, in order to draw shear force diagram and bending moment diagram, I will have to draw guidelines. These are the guidelines on which I'll draw shear force diagram and bending moment diagram. Okay. This is the 0, 0 line. And we are going to draw shear force diagram, which is abbreviated as SFD, and the units that we will consider are kilonewton. Okay, we will draw another guideline under the point load because there will be variation in SFD and BMD under this point load. Okay, what was our nomenclature? Okay, we did not call this point as B, we call this as C, and this point is point B. Okay, now at point A, or for portion AB, what was the value of shear that we calculated? It was equal to 5 kilonewton. So we will draw a line showing a constant value of 5, right? And these SFDs and BMDs will be drawn on rough scale. When I say rough scale, I mean we will not be choosing any exact scale and drawing the lines according to that scale. Rather, we will be drawing them on rough scale, meaning that the bigger values should appear to be bigger on the diagram, but these values do not need to be on some exact scale. Okay. For portion AB, the value of shear is 5, and then for portion BC, the value of shear is minus 5. So how did we incorporate this minus 5? We incorporated this minus 5 by drawing this 5 below the 0 line. Okay, because this value was negative, V was negative for portion BC. So we have plotted it on the negative side of the of the axis. So this 0, 0 line, positive side is on the upper side and negative is on the lower side. And the shear force diagram and bending moment diagram will always close. By closing, I mean it will come back to 0. You can see that we have ordinate of 5 here, and there is a 5 kilonewton reaction acting here that will bring the diagram to 0. Similarly, we have a 5 kilonewton reaction here. So this part of shear force diagram is positive and this part is negative. This is shear force diagram for the simply supported beam. Now let's draw the bending moment diagram. 0, 0, and we are going to draw bending moment diagram, and the units will be kilonewton meter. Okay. Now, what is the value of bending moment at point A? The value of bending moment at point A is equal to 0. And what is the bending moment at point C? It was also equal to 0. How much was the bending moment at point C? At point B, it was 25 kilonewton meter. 25. We have written the units here, so we do not need to write down unit with every value on shear force diagram and bending moment diagram. So this is 25. So we have marked the ordinate. Next question is that how should we join these points from 0 to 25 and 25 to 0? Should I join it with a straight line or with a curved line, convex up or concave up, or what? For that, we will have to look at the equation of bending moment for these portions. Now, let's see the equations. This is the equation of bending moment for portion AB that we just discussed. How much is the degree of this equation? M is equal to 5x. How much is the power of x? Power of x is 1. So if power of x is 1, it means that it is a linear equation. So the line joining point A to B should be a straight line, should be a linear line or first degree line. So it should be something like this, a straight line. Similarly, for portion BC, this is the equation of moment for portion BC, 50 minus 5x, and this is a single degree line. So we should join this point with this point through a first degree line. Here it is, a straight line without any curve. So this line is first degree. Similarly, this line is first degree. With straight lines, you do not need to write down the degree. I've just written it for clarity. Although when we will be drawing curved line, you will have to write down the degree with the curved line, because in some cases we will have second degree line and in some cases we will have third degree line. Anyways, so this is the bending moment diagram, and the entire bending moment diagram for this beam is positive. This bending moment diagram for this beam. Now, if you recall, our convention for bending moment is, we said that sagging, this type of bending is termed as sagging, and our convention is that sagging is positive, and this type of bending is termed as hogging. sagging is positive and hogging is negative. This is the convention that we are following. Last step is to draw the elastic curve. For that, we need to keep this convention in our mind. Sagging positive, hogging negative. The entire bending moment diagram is positive. It means that the beam is sagging down. And plus, this beam is within the elastic limit, so there will be no sharp bends in the elastic curve. The elastic curve will be a smooth curve. Even if we are going through a transition from sagging to hogging or hogging to sagging, the transition will be very smooth. Okay, so let me now draw the elastic curve. The elastic curve of the beam will be somewhat like this. This is the elastic curve, a smooth curve showing the deformed shape. This is okay. So this is not actually a straight line. This is a curve. Sorry for bad drawing. But this is a very smooth curve representing the elastic curve of this beam. So this completes solution of our first problem. If you have any questions, I will be taking your questions in our class meeting. So I will stop recording at this point.